here we're going to talk about continuity and what it means for a function to be continuous. So we'll start with a definition. F is continuous at a point A if the limit as x approaches A equals f of A, and they're not infinities. So f is continuous at a point if the limit as x approaches A equals the function evaluated at that point. And we've seen many examples of this. We've also seen some examples where this isn't true with those. It might be good now to look at some of the graphs from the beginning of the limit discussion. Most of them were continuous. The last one was not. One convenient graphical interpretation of this definition, which I'm not going to write down, but I will state, because it is good to think about sometimes, is a function is continuous at a point if you can draw the function through that point without lifting your pen. And this just says continuous at a point. If a function is continuous at all points, then we call it a continuous function, which I'm not going to write because it's basically the same as this except just at all points. So a function is continuous everywhere if you can draw the entire function without lifting your writing implement anywhere. So most of the graphs we've seen have been continuous. Some of them haven't been continuous, and we'll talk about that in a moment. But let's first, one of the things we'll do will be to check functions for continuity. And to do that, we need to check the limit on the right and the limit on the left. We need the limit on the right to be the same as the limit on the left, and we also need that to be the same as the function evaluated at that point. Because remember, this limit will be some number if it's the same limit on both sides. So before doing that directly, let's look at some examples of where continuity can go wrong. So example. This example covers possible discontinuities. So if a function is not continuous at a point, we would say it's discontinuous or it has a discontinuity at that point. Yeah, that's spelled right. It's okay. So I'm going to draw a graph. And I'd like it to fit all on one of these. Okay, maybe I should move my y-axis because I don't want it to go onto that next board. There, that's better. Okay, so we have that. We have this. And we have, let's just draw it like that. And let's label some points. Let's throw an arrow on that. Let's call this one, let's do odd numbers here. That asymptote's at 7. What's an asymptote? That's at 2. That's at 4. And let's throw another point up here, and let's make that 6. And let's call this F. We'll cover asymptotes in the future. For now, that's an asymptote, something else like that. So right here, this example covers 3 different types of discontinuities. Now, using that writing implement remark, right here, once we get to 3, we have to move our writing implement. So this has a discontinuity at 3. Similarly, at 5, you have to lift your writing implement, and at 7, you have to lift your writing implement. So let's, how do I want to write this? Let's write it like this. Here, f of x is not continuous at x equals 3. And I'm going to leave a gap between each of these because I'm going to write a couple things here. At x equals 5, and it's not continuous at x equals 7 from the writing implement remark. But what is the reason for that using the limits? Because Because we know limits, we should describe things using limits. Well, what happens at 3 to prevent that equality from holding? Well, the limit on the left, I need to mark another number. Yeah, I do. I did over here. Let's make it -4. Let's make it an odd number. -9. Not drawn to scale. So why is this not continuous at 3? Well, that limit doesn't exist because the limit on the left is 4, but the limit on the right is -9. So let's say limit as x approaches 3 from the right of f of x does not equal limit as x approaches 3 from the left of f of x. And this actually is not enough room. I'm going to write one more thing under this in a moment. So if you're taking notes, leave an extra gap here. I'm going to write some words there. What about at x equals 5? So let's say since. Since. What happens at 5? Well, the limit as x approaches 5 is 2. Because the limit on both sides is 2. But f of 5 is 6. So we'll say that this is discontinuous since limit as x approaches 5 of f of x does not equal f of 5. This limit is 2, while f of 5 is 6. And again, I'm going to write a word there. I'm going to write some words there. And what happens at 7? Well, this limit can't be a positive or a negative infinity on either side. And I'll be a little informal with that. It's discontinuous at 7. Let's just say since limit as x approaches 7 from the left is positive infinity. The limit as x approaches 7 from the left is infinity. If on either side you get either infinity, it's not continuous. Now, this illustrates the 3 discontinuities we will cover. So we describe these using words. So I'm going to just write that in here. I really don't like how this looks on the board. Hopefully in your notes it looks a little better. So I'm going to call this first one, when the limit on the left does not equal the limit on the right, we're going to call that a jump discontinuity. When the limit on the one side is different than the limit on the other side, we call that a jump discontinuity. In this next one, where there's just one point preventing us from being continuous, so where the limit exists but the function isn't that limit at that point, we call that a removable discontinuity. Discontinuity is a really large word. Call that a removable discontinuity. And this next one, where the limit on one side of the number, or both sides, is a positive or a negative infinity, we just call that an infinite discontinuity. And I'll squeeze that down here. I-N-F-I-N-I-T-E, discontinuity. So if the limit on one side of the number is an infinity, or negative infinity, then that gives us an infinite discontinuity. So we have these 3 discontinuities. They can be described with limits, as we do here. And if you are talking about discontinuities, it's much better to describe them using limits than it is to describe them by saying, well, I have to lift my writing implement. Why, you might ask? Well, take an advanced analysis class. The definition of continuous and the definition of limit that we discussed in Calc 1 are not the real definitions of continuous or limit. if we did give you the real definitions, it would quite likely lead to your dislike of calculus. So we talk about them in more convenient graphical ways. You can look up the actual definition of continuous. If you see something, if you look it up and you see something that looks like this for continuous, that is the correct definition. And if you see something that looks like this, if you look up the real definition of limit, section 2.5 of our textbook for the limit, that is the true definition. But we're not covering either of them this semester, unless you want. So we have these three types of discontinuities. Most of the functions we're going to deal with are continuous, or at least are continuous on their domains. And I'm not going to write it as a theorem, I'm just going to state it, and then we'll do a couple examples. Polynomials, rational functions, root functions, trig functions, exponential functions, logarithmic functions, addition of them, subtraction of them, multiplication of them, division of them, and multiplication by a constant of them are all continuous functions on their domain. So let's just look at two examples. On which intervals is each function continuous? Oh, that's a terrible spelling. C-O-N-U-T, that's not even close. C-O-N-T-I-N. Now, when I'm writing words, I sometimes misspell them because, I'll start writing a word and then I'll say another word. And I find it pretty hard to speak and write correct things at the same time. You can see how I botched that sentence. I was probably erasing and speaking at the same time. But if you have time during our 4-week class, just try writing a word while saying a different word. See how it goes. Hopefully you are better at it than I. So on which interval is each function continuous? Let's look at two of them. So we'll look at these two. On which interval is continuous? Well, the theorem I just said that all of the functions that we're going to be dealing with are continuous on their domains. Unless it's piecewise. I didn't say piecewise. So right here we just have to find the domain. Well, this is a rational function. A rational function's domain is everywhere where the denominator is not 0. So where is the denominator 0? So denominator equals 0 when what? When x equals 5. So f of x equals x plus 1 over x minus 5 is continuous everywhere except 5. So on negative infinity up to 5, jump over 5, and 5 to infinity. This would be an infinite discontinuity. You could use a limit argument because you get a number over 0 at 5. But we won't do that now. So this is continuous on those intervals, everywhere but 5. What about this next one? Well, it's a root function. Root functions are continuous on their domain. Where is the domain of a square root? Well, in order to take a square root, what's inside the square root must be positive, or 0. So to do this, we're going to set the inside of the square root greater than or equal to 0. There's a slight inconsistency in these two arguments. Here, in the first one, we're finding the bad points. Here, we're finding the good points, but our final answers will be the same. Where is x squared, or 16 minus x squared larger than 0? Well, add x squared to the other side, when x squared is less than or equal to 16? Well, this is going to happen between 4 and negative 4. At 4 and negative 4, you get equality. Less than 4, but larger than negative 4, you get a square smaller than 16. You can like check 3 and 2 and 0 and all those numbers. Anything above 4, the square is larger than 16. So right here, this is the domain. But we should use interval notation, so let's do that. So we'll say, so f of x equals root 16 minus x squared is continuous on negative 4 to 4. That's a period, not a line. Including both of the endpoints, because square root of 0 is okay. And let's look at 2 more examples before covering our final theorem. Before doing that, what is this a graph of? Without using electronics, what is this a graph of? If you use electronics, that's just a waste of time. Man, maybe it's not for this one. For others it is. You see a graph of this using electronics, that might actually help you see what it is. But in general, you should avoid electronics if you want to learn math. Very important. You never know when electronics prevent you from seeing something useful. Important. What is this a graph of? What if I rewrite it? Maybe that'll help. I don't know if that helps. What if I rewrite it like this? Well, that's not identical. We took a positive square root here. So the only y's we can consider here are positive y's. We can't consider negative y's because square roots don't evaluate to negatives. What if we rewrite this? What is that? Well, with this restriction, that's a semicircle. So this right here is the graph of a semicircle. If you wanted the full circle, you couldn't describe it as a function. You can only describe it as an equation relating x and y. So if you wanted to describe a full circle, not a function, but it would be the set of x and y which satisfy that equation, the circle of radius 4. But if you throw the square root on it to make it a function, you can only take the top half, because vertical line test fails. Circles are important. I like circles. Those two comments are not necessarily related. Where are we? Let's do 2 more examples. Example. F of x. I'm going to tell you something and then we're going to show why. F of x equals negative x squared plus 4 when x is less than or equal to 3. 4x minus 7 when x is larger than 3. So here we have a piecewise function. In that list of functions which are continuous on their domains, piecewise functions were not included because piecewise functions aren't necessarily continuous. So right here, we're going to show that this is not continuous at x equals 3. Notice it's continuous everywhere but 3, because it's just a polynomial on the one side of 3, it's a polynomial line on the other side of 3. But at 3, this is not continuous. And how will we be able to conclude this isn't continuous? Well, we're going to conclude that at 3, it looks something like that. meaning we're going to conclude that the limit on one side of 3 is different than the limit on the other side of 3. And we'll use our function to help us do that. So limit as x approaches 3, let's do the left side of 3 first. On the left of 3, this function is defined as negative x squared plus 4. We're going to evaluate this by substituting 3. We get negative 9 plus 4, which is negative 5. Okay? So for this to be... Oh, okay. I've looked at that too quickly. For this to be continuous at 3, the limit as x approaches 3 from the right would have to equal 5. But let's find what the limit as x approaches 3 on the right is. Limit as x approaches 3 on the right, this piece of the function defines what happens on the right of 3. Now I can actually get rid of this sign up here. I will. Because once we substitute what happens on the left, we don't need to worry about the sides anymore. Limit as x approaches 3 on the right, it's defined as 4x minus 7 on the right of 3. Substitute 3, use the limit laws, 12 minus 7, which is positive 5. So this is not continuous when x equals 3. And I'll just say up here, maybe I'll say it down here. I was going to say since limit on the left doesn't equal limit on the right. So we'll just say since limit on the left of 3 of f of x does not equal limit on the right of 3 of f of x, f is not continuous at x equals 3. That says continuous. So if we went through this and we got that these limits were the same and we were correct, then we would be showing that it is continuous at 3. But we went through this, we got different numbers. 5 and negative 5 are not the same, last I checked. So function is not continuous at 3. Let's do one final example, a different example. Find the value a which makes f of x continuous at x equals negative 4. Find the value a which makes f continuous at x equals negative 4. Again, it'll be piecewise. So we have 4x squared minus 7 when x is less than or equal to negative 4. And we have 2ax plus 3 when x is larger than negative 4. Find the value a which makes the function continuous at negative 4. So remember, continuous, to show continuous, we need the limit on the left to be the limit on the right to be the function at that point. That last equality is taken care of by having one of these be less than or equal to, or greater than or equal to. So all we really have to check is what happens on both sides of negative 4. So let's do that here. Limit as x approaches negative 4 from the right. Maybe I'll do the left first, since that's how this is written. Of f of x. Which one is the left of negative 4? Here's negative 4. Here's the left of negative 4. So the first one. Whenever dealing with left and right with negative, I usually don't draw one. I usually visualize a number line. There are things where I have to draw, like doing any trig evaluations, I have to draw things, but just for this I picture a number line. Where were we? Left of negative 4 is defined as this function, so this equals this limit of 4x squared minus 7. And we can just do a direct substitution here. It's just a polynomial. We get 64 minus 7, because what? We get 4 times 16, which is 57. Okay. Now we need the limit on the right of negative 4. Well, this function tells us what happens on the right of negative 4. So 2ax plus 3, I should probably put those in parentheses. Because the way it's written, that 3 and this negative 7 aren't in the limit. As x approaches negative 4, let x equal negative 4. What do you get? Let x be negative 4, not a. So we get negative 8a plus 3. Now, why did we do all this? Well, what will make this function continuous at negative 4? It'll be continuous at negative 4 if what happens on the left is the same as what happens on the right. So we'll say f, lowercase f is continuous at negative 4 when these are equal. So when 57 equals, where are we? Negative 8a plus 3. And we just need to solve this for a. Subtract 3, you get 54 equals negative 8a. Divide by negative 8. You get 54 over negative 8, which reduces to what? Do you get rid of a 2 from everything? So negative 27 fourths. So a equals negative 27 fourths. That's a 4 in that denominator. So this type of example will show up. It's a good example for understanding the actual definition of continuous. One last remark. I'm just going to state this because I don't really see value in writing it. Yeah, I do see value in writing it now that I look at it. Because we're going to do an example. It's not a remark actually, it's a theorem. And it tells us that we can take lots more limits than we've been able to take. Theorem. If f is continuous at L, notice we're using L there instead of whatever other letter we've been using, A. If f is continuous at L and limit as x approaches A of g of x equals L, then what? Then limit as x approaches A of a composition. Compositions are very important in calculus, especially late next week. Late week 2. So if f is continuous at L and the limit as x approaches A of g of x is also L, then the limit of f of g of x as x approaches A is f of the limit of g of x as x approaches A. Meaning, if we have a composition of functions, all we need is a continuous function on a domain in order to push this limit inside the composition. and this equals f of L, since that's L. Now, how can we use this? Well, let's look at an example. We couldn't take this limit before this result. We couldn't take the limit I'm about to write, I should say, without this result. Let's make it pi over 4. Why not? Limit as x approaches pi over 2 of cosine of x minus pi over 4. How can we do this? Well, we can't use algebraic limit laws yet. What we can do, cosine is continuous on its domain, which is everywhere. So we can push, using this theorem, this limit inside. See what we did there? We have the limit of cosine of something, and with this theorem, we can then take this limit and put it inside the cosine. So we have cosine of the limit. And now, in here, we can actually evaluate that limit. We haven't taken cosine yet, so we still need that. The limit as x approaches pi over 2 of x minus pi over 4 is just pi over 2 minus pi over 4, which is pi over 4. Half minus a quarter is a quarter. If you have 50 cents and you spend 25 cents, you have 25 cents. So this limit equals cosine of pi over 4. What's cosine of pi over 4? Well, pi over 4 is quadrant 1, so cosine is positive. We need our pi over 4, pi over 4, pi over 2 triangle. If we don't have a chart of things memorized, which I don't. Cosine is adjacent over hypotenuse. Quadrant 1, so it's positive. So we get 1 over root 2. So this theorem right here allows us to view many, many more limits as a direct substitution. Because here, if you try a direct substitution, you would get what we have at the end. So try there's probably one continuous continuity example on the worksheet, maybe two. I don't know. I haven't written it yet. So see how they go. And if you have questions, we have a workshop on Thursday. I think it's the 7th, from whatever time I wrote on the syllabus, 11 to 12:30, I think. So I hope to see you then.